So thank you very much for the introduction. And today I will talk about a joint work with Charles Bordenave. So the paper is on archive. There will be more about it, but most of the talk will focus on this. And so it's about, so let me try to pick up where Ben stopped. So, there is this, how was it called? This probabilistic, this random matrix version of the Peterson Thom problem. So I will quote it I will write it as a question. So let's say I call gamma the group which is the product of the Cartesian product of two or three groups with degenerators. So which I will call maybe A1 AD and then B1 BD, and we pick a random representation, random finite dimensional representation of gamma. So a random finite dimensional representation of gamma on Mn tensor Mn as follows. So we say that AI is going to be sent to UIN tensor identity, and BI is sent to identity tensor VIN, where the UIN and the VIN are all, there are two N independent Haar distributed random matrices. So this gives me a random representation of gamma, and so in turn this also gives me a random map from the group star algebra of gamma to Mn tensor Mn. And I will just take a bit more of notation. So I will call this phi n, this random map. And if I have any element there, its image, I will just call it Pn. So this is phi n of P. So the point of view which I take is that it's a random matrix model indexed by the dimension. And so the question is, let's see. Maybe I will. Is to try to understand the behavior of the operator norm of this random matrix, and namely, is it true that almost surely the limits as n goes to infinity of this, the operator norm of this goes to, so maybe it's a question, the operator norm of P viewed in the reduced group C star algebra. And so if, as Ben explained us, the motivations come from Feynman algebra theory. So this is it implies the Peterson Thom conjecture. And so maybe first one comment is that, or maybe one observation is that. So I retake the problem from the point of view of random matrix theory, and it is simple. It's very simple. It's reasonably simple to show that the limit inf as n goes to infinity of the operator norm is bigger than p, than the operator norm of p in the reduced group algebra. It just follows actually from Voiculescu's asymptotic fairness. I mean, it's a little bit more, but basically, knowing that independent Haar unitaries are almost surely asymptotically free implies that the p norm of this goes to the p norm of this, and when you take the limits appropriately, you obtain this observation. So it tells that the hard question is actually so. If we have a limit and whether the limit sub is less than p, that's the question which one really cares about. And so the answer to this question is yes. To this question here, and this is, as far as I can tell, there is no published answer yet, but it has been announced by many people. So it was first announced by Belinsky and Kapitein. So then it was announced by Bordenave and me. And then by Chen, Garza, Vargas, Trop, Van Handel, and two more people, De La Salle, Maggie, and Parot. So there are, well, 5 different proofs. Maybe none of them are published as far as I can tell. So I wanted also to add, so this is the chronological order, I think. Is it the chronological? Did I mess?
Reverse the last 3.
The last 2.
Yeah, so put us on the bottom.
Okay. Okay. Anyway, so it's not the. It's the chronological order up to here.
Wasn't that the paper that I wasn't on?
That's the paper you weren't on. So we have a paper where we have a method which was used by Nagy and De La Salle together with other stuff.
Okay. You know, somebody told me yesterday that when you get a proof that you understand, you stop. You stop following the history. Anyway, but what is very interesting is, the proofs are, all the proofs, some proofs are very different and some proofs are really different from each other. So, of course, this paper here is that one, so I would like to say a little bit about that proof. But actually, I think that for the purpose of Peterson Thom and this very question, actually, I think that the proofs which are later are easier and more efficient. So I will still speak about that, but about also, like, if I have time to go into details, I will speak about some other interesting details of this paper. So let's see. Right. So actually, what we look at is so what I could call a superseding problem that we look at is the following. So I will use some funny notation where I will say that u minus I, so that u0 of n is the identity. And u minus I of n is ui n star. Okay? And then the problem in which I'm interested is I look at the following random matrix, sum for I between minus d and d of ui of ai tensor u I d, where so this is an n by n matrix, and this is k by k matrix, let's say. And so these are any coefficients, and I would like to compare the operator norm of this, which is a real valued random variable, with what I suspect to be its limit, namely sum for I between 1 minus d and d of ai tens ui, where ui are actually, for me, the generators of, these are the generators of the group reduced C-star algebra of the free group. So this guy, which maybe I will call Zn, is a random matrix, and this one is a number, and this is the norm of an operator which belongs to the k by k valued elements of the C-star algebra. And maybe I should say one word. I mean, I think most of what I'm saying is elementary when one comes from operator algebra, but coming from random matrix theory, it was quite enlightening. So I will just say it. So why does this problem supersedes this one? It's because of two reasons. So maybe a difficult one and a hard one. The first one is PZS linearization. So PZS linearization says that if I want to understand if I take an element of the group algebra of the free group, so I do the same, but not with two tensors, just one. What we have is that the operator norm, and I take and then I take a representation. Well, it could be any group anyway, but okay. I take a representation in a finite-dimensional representation, and again phi n, and then this is going to be phi n of p is Pn. What we have is that the operator norm of Pn tends to operator norm of P if and only if the operator norm of this operator, if and only the operator norm of Zn tends to the operator norm of Z, and that would be here. So this is true for all P here, if and only if this is true for all K and for all A minus D, AD in the K by K matrices. So understanding this problem is good enough to understand, to linearize, to turn a problem which involves polynomials into a problem which does not involve polynomials. Well, actually, here any group would I mean, this is just a C-star algebra statement, and then maybe I will just say a Fubini. So actually, so Fubini's theorem, which is that here you have some UIs and some VIs. So let's first consider VI. Let's just condition over VI, and if we can work over UIs, and we have a good norm estimate, then we could integrate out again over UI after. So I'm not going into every detail, but like here there is only one random. There is randomness only over one leg, but if we can do it, here for many AIs, so for maybe k large enough, for k grows to infinity with n in a sense which I will precise later. And so, so specifically, what we would, so we are interested in the following problem. So if I look, so I want to compare, to be a bit more specific. So I have this Zn here. And I have what I suppose to be its limit. And I would like to check how far away it is from the limit. So maybe I can write something like this, bigger than epsilon times norm of Z. And we want to estimate. So given epsilon positive, we want to estimate this. So, and what is known is that if k fixed n goes to infinity, this quantity goes to 0. It follows from what I did with Mal some time ago. Let's see, right. So if we could, for example, have something like k grows at the same speed as n to infinity, then this would. So if the same is valid for k grows to the same speed as n to infinity, then Ben's question is solved. Then here, so I would like to spend a bit of time on discussing this question. What is known? What is known, not very difficult to show, is that if k is extremely big, or maybe I could say even k equal infinity, then it's false. Then this estimate is false. You can actually easily cook up some example. I think if k is bigger than maybe exponential some constant times maybe d times n squared, I think. So roughly speaking, the counterexample relies on the fact that the operator norm of sum of ui bar times ui for maybe here I between minus d and d. So this relies on the fact that this has always norm 2d plus 1. So here you would say, well, this is random. What am I talking about? And what you could do is you could just take a big net, so maybe a big direct sum of diagonal matrices, and at some point, if they approximate the UI, then the operator norm will be too big, because that quantity, if we wanted this to be true, should be of the size root d. So this is bigger than root d. So that's a that would not work. A really important question is well, how far does it goes, and maybe I will write a little bit more here. Somehow we were making, if I should say, like linear or polynomial progress. So I think that at some point we had maybe k is n to the 1/3, and then there was like k is n to the 2/3, and then maybe there was k equals n to the whatever, n over log n, something like this. So there was some. Anyway, it looked like this was hard to attain somehow. It looks like this threshold was hard to attain. And what Charles and I proved is that, let's see, where shall I write? Okay, I will write here. So theorem. We put the estimate holds maybe for a k which is of the order of something like exponential n to the 1 over 100, something like this. So we had some 1 over, this is 1 over, yeah. Yeah, it depends on d, maybe, so plus, I forgot, plus 60d or something like that. So there is a dependence in, but the point is, if you fix n, okay, let's fix n. Let's fix n, and so this is, okay, maybe this is exponential n to some function of d, which is strictly positive, is the result which we obtained. So in particular, this solves this problem together with linearization and this Fubini integration trick. So, right. And so how does there is one more part in our paper which I would like to speak.
If I can ask a super quick question. So you related somehow this question of Ben, which with AI being random, right? So you have like
Yes.
EI tensor UI, two of them, with a growth rate of A being of order n.
Mm-hmm.
Does that extend further? That is, if you have like tensors of length 50, or let's
Yes.
say like 50, then it just gives you a different growth.
Yes.
And what is the growth rate then?
So what we had, I think we had something like maybe log of the number of legs or something like that. We had the number of legs could also grow at some pace, but they are like much. I think there are very much better improvements. I mean, so you yes, yeah, you can do all this through linearization. So yeah. Right. And all right. So so here, one thing that we have though is that so in addition, maybe I should say, so in addition, we have that the limit inf as n goes to infinity of the operator norm of Zn is always bigger than the limit, the operator norm of Z, and this is for any k. So somehow the upper bound clearly, there clearly has to be a threshold for the upper bound, but I mean, to my surprise, there was no constraint on the lower bound. This estimate works all the time, and so I would like to say a little something about that. But perhaps, right, so before getting into, that, so if you have that, by the way, maybe a small remark for people who are interested in graph theory is that this gives maybe a generalized along Bopana bound. So the along Bopana result says that if you have a regular graph, then the second largest eigenvalue is at least what you get with free probability theory. And here you have like a covering version of this, which is implied by that. And you don't even actually need randomness for this to hold. So this is a corollary of that result. So in general, maybe I should still say one word about how to prove these results, because maybe it will anyway shed some light on some interest on how to work that out afterwards. So the strategy for the upper bound, I will just outline it briefly. It's basically the moment method. It's a moment method. So basically, what we have to do is we have to compare so we have our z. Maybe I'm going to assume with sort of generality that z is self-adjoint. And then we have to compare the trace of this to the power q. So compare. So we have to compare the expectation of trace of this with the expectation of tau in the limit of z to the power q, and that would be for q which is bigger than log of the dimension, so log of k times n, and that looks like a very crazy thing to do, and we didn't know how to do it until maybe 6 or 7 years ago, at least in the case of multi-matrix models. But so here I won't get too much into details, but so in our first joint work with Bordenave, we used something which we call non-backtracking operator valued version of z. So we transformed z into something which is a version of a non-backtracking operator in graph theory, and then some slightly delicate Weingarten estimates. And in our most recent paper, which I'm talking about today, we actually replaced this by, so we don't need anymore this. We have somehow a more direct, so we change more direct moment method. We have a way to group moments along the tree with some last visiting times, which somehow captures the combinatorics behind our non-backtracking operator, which makes things work. So the point is that we need moment estimates, and moment estimates require something like that. So there is no chance that that any quantifier like this would work somehow. So how to get these results? And here we need to use exactness of the reduced C-star algebra of the free group. So, but in a and so of course the exactness of the reduced C-star algebra has been used quite a bit for strong convergence. It has been used by Hagerup, Torbjörnsen. It has been used by Dima and Camille, Felix, Alice, and I also use it. But it was some. I mean, in my understanding, it was the somehow the original definition of exactness which was used. And here actually we use something which is slightly different. And again, I think all what I'm going to say from now on is very trivial for operator algebraists, but it was very enlightening from the point of view of random matrix theory. So I would like to say a few details about it in the last few minutes. So what we have is we have the following. I don't know, maybe it's a lemma. I don't know how you could call it. So if you call it the way you want, but that's what I would like to present from maybe chapter 4 or 5 of our paper. So you pick some, you pick some operators A minus D, AD, which belong to any bounded operators, and I don't make any assumptions here on H. And you take, and then you create your operator, some I between minus D and D of AI tends QI, so which here is going to belong to the minimum tensor product of B of H and the reduced C-star algebra of FD. And there exists, and so you take some positive epsilon, and there exists an n, which depends on epsilon, and there exists a self-adjoint projection P of rank n, such that 1 minus epsilon times the norm of Z is less than the operator norm of P tends 1 Z P tends 1. So what it means is that you have this big space, you can cut it. And now what you have is you have a finite dimensional matrix. So this is here. So now I could think of it as a matrix which belongs to Mn, tens M. So now it still belongs here. But what I will do for future use is to replace this by Mn times M capital N. And then, so if I have this, let me just first say what I can do if I have this. If I have this, so the P, what is important is that P, yeah, I should have said that P is actually depends explicitly on AI. So if you give me AI, I can construct P. It depends on AI and on epsilon, I should say. So if I have this, then I cook up my P, and then to have a lower bound, I will just first I will take the random matrix. I will represent it as a random matrix. Then I will cut, and now the dimension the problem of having k that grows to infinity is gone. So I don't even need to have the lower bound. I don't even need the strong convergence. I just need the weak convergence. So to conclude, weak convergence. So Voiculescu's result is enough. Becomes sufficient. And the way you do this is by actually it's Ozawa, my colleague from Kyoto, who taught me this trick. So now what I will do is I will look at the reduced star algebra of FD as living in B of L2 of FD, and I will take one more notation, which is L2 of FD with an L here. This is the words of length less than L, of reduced length L than L, and I will say that pi L is the finite rank projection, orthogonal projection onto this Hilbert subspace. And then what you do is you create a map which goes from the following subset of B of L2 of FD to this finite this matrix algebra, so it goes from the span of UI, so which is an operator space. So it's a 2D plus 1 dimensional vector space, which is a self-adjoint and which contains the unit. So I will call it maybe phi L, and it goes from here to there. And to UI, it just associates the truncation, pi lambda UI pi lambda. So this map is actually a bijection, a linear bijection, as soon as what? Maybe L is bigger than 1. And I think 1 is enough. So I can look at its inverse, and the fact, which is non-trivial in my opinion, is that is that if I compose this map with its inverse, so the completely bounded map tends to 1. So this is an almost a quasi-isometry as n goes to infinity. So actually, an operator space characterization of exactness is to have a quasi isometry in finite dimensional matrix spaces. So here, this is just an explicit construction, which happens to work. And then once you have that, you are done, because maybe I will write here how. Maybe I will finish the proof here, and then I'm not using more than this blackboard. So what you do is you consider your operator Z, and to it you apply phi L and the identity of BH. So maybe I will call this guy ZL, okay? And then you pick an element X in H tens L2 of F DL, such that X star ZL X is bigger than 1 minus epsilon X star X. So you approximate the norm. Then you do the singular value decomposition. So X, because this is finite dimension. So you write that X, this is sum of EI tens Fi. And this is a finite sum here, because we have something finite. and then the P which I announced here. This is the projection onto the span of EI. And that's with a 2, there is a 2 epsilon which is going on here. And so this finishes the proof. And it finishes my talk as well.
Thanks, Benoit.